The last section here in chapter 6, we are going to graph radical functions. Now, we know what quadratics look like. We know what parabolas look like. In the same way that we can transform them in absolute value graphs, we can also transform our other parent functions with radicals. And those two parent functions are y equals the square root of x and y equals the cube root of x. Again, those same transformations can apply. So let's take a look first and see what this parent function looks like. Y equals the square root of x. If you imagine you take 0, plug it in for x, square root of 0 is 0. That's our first point. Square root of 1 is 1. The next number we can square root nicely is 4. So we'd have 4, 2 on our graph. Now, this graph of the square root of x only continues in this direction. The reason for that, imagine if you take a negative number and plug it in for x, then we have something imaginary because we have a square root of a negative number. So this is what my parent function looks like for the square root of x. Cube root of x, try to visualize for a second what y equals x cubed looks like. Okay, that was this shape. Y equals the cube root of x is kind of similar but flipped on its side. The cube root of 0 is 0. The cube root of 1 is 1. The next number we can cube root nicely isn't until we get to 8. My graph here only goes up to 6, so I'll extend this a little bit more. The cube root of 8 is 2. Okay. But we can cube root a negative number. The cube root of negative 1 is negative 1. Negative 1 times negative 1 times negative 1 is negative 8, or negative 1. But then we can also cube root negative 8 here. Again, we only go out to negative 6, extend a little bit beyond. Negative 8, negative 2 would be another point on our graph. So I usually like to turn my paper sideways when I'm connecting the dots. It can be kind of awkward to connect these points because it's so long and skinny. But the cube root of x has this kind of S shape, like our x cubed function looks like. Okay, again, we can transform these functions the same way that we've transformed quadratics and absolute value throughout the year. So let's look at example 1a. We will transform a square root function. So we're going to graph y equals 2 times the square root of x plus 1 minus 2. Okay. I'm going to put my graph on here. That was a little crooked, but not too bad. Now to graph my square root function, I'm going to make a table of my parent function. And if we look up here, square root of 0 was 0, square root of 1 was 1, square root of 4 is 2. We want to make sure that we are transforming these 3 points and including these 3 points on our graph. Now if we look at our transformations here, this plus 1 inside is going to move our graph left 1. Those same transformations we used first semester, they're coming back again. And this isn't the only time. We'll see them again throughout a second semester. We're transforming our graph left 1. This 2 out front is a vertical stretch. And this minus 2 at the end is going to translate our graph down 2. So let's change our table accordingly. Remember, your transformations follow the order of operations. So we have to go left 1 first. That's going to affect our x values. Subtract 1 from each. This 2, our vertical stretch, affects our y values. Multiply each y value by 2. And then we have to translate our graph down to. Subtract 2 from each y value. Now all that's left is to put these pieces on our graph. So we have the point 1, -2, or sorry, -1, -2, 0, 0, and 3, 2. Okay. Keep in mind that the graph does not extend past this point. Okay. So our graph is going to keep going to the right, does not go forever both ways. And some of you guys might not necessarily have to make this table. Some of you got pretty good at just kind of thinking through your transformations and how that was going to affect based off the equation and based off your parent function. So if you're okay with that, keep going with that. That's totally fine. But that's graphing a square root function.